Good day to everyone. Today we'll be discussing about pure axial compression. So we have two general categories for columns. First is the solid columns. So examples of solid columns are interior building columns, struts, studs, and truss members. Meanwhile, built-up columns are made up of individual planks or laminations joined mechanically by through bolts or nails. So there are also two types of columns according to column length. First is the short column, wherein it implies that a compression member will not buckle, and the strength depends only on the crushing or material capacity of the wood. Meanwhile, for long column, so buckling occurs before the column reaches the crushing or material capacity, so equal to F prime C 8. Strength is a function of the slenderness ratio of the member. So for pure axial compression, the basic design equation for axial compression stress parallel to the grain is given by F sub C is equals to P over A should be less than or equal to uppercase F prime C, where F sub C is the actual or computed axial compressive stress parallel to the grain. Meanwhile, P is the applied axial compression force, A sub G is the cross-sectional area of the member, and uppercase F prime sub C is the adjusted allowable compressive stress parallel to the grain. So uppercase F prime sub C is given by the base design value uppercase FC multiplied by C sub D, C sub M, C sub T, C sub F, C sub I, and C sub P. So for getting the actual compressive stress parallel to the grain, do we use the gross area or the net area? So assuming that there are no bolt holes in the column except at the supports or end connections, then the compressive stress is computed as first is away from the supports where buckling is a factor. So F sub C is equals to P over A sub G should be less than or equal to uppercase F prime C, where C sub P is applicable and we need to check for column stability. Meanwhile, for the second case wherein the, at the connections wherein the buckling is not a factor, F sub C is equals to P over A sub N should be less than or equal to uppercase F prime C, wherein C sub P is not applicable. So for column stability, slenderness ratio, for certain column or compression member, buckling only occurs in one axis. So it is determined by the governing slenderness ratio. So in general formula, the slenderness ratio can be computed using L sub E over R, or for rectangular sections, we can use L sub E over D, where L sub E is the effective unbraced length, or simply effective length. So it can be solved by multiplying K sub E multiplied by L, where L is the unbraced column length about the axis of the buckling. So for K sub E, it is the effective length factor, and the variable R is the least radius of gyration of column cross-section, and variable D represents the least cross-sectional dimension of the column. So it is also the dimension of the column section perpendicular to the axis of the buckling. So first, for example, we have a column here. So it is braced on both sides in the X and Y axis. So if you consider buckling at the X axis, as you can see here, the buckling will occur in this way. So the variable D, which is the dimension of the column perpendicular to the axis of buckling. So if we have buckling along the x-axis, then our variable D sub x will be this length. Meanwhile, for buckling along the y-axis, the column can buckle in this way. Okay. So the variable d at the y-axis, or representing the variable d representing the bending about the y-axis is this dimension of the member. Okay. So if we're given a column where it is supported along the top and bottom parts, as well as there is a support, lateral support along the y-axis, so the bending along the x-axis will still be the same, single curvature all throughout the section. Meanwhile, for the bending along the y-axis, we will have a two curvatures. Since the lateral support will prevent the column to buckle along the y-axis, so the deflection at this point will be 0, and we will have two curvatures for the bending along the y-axis. So we have a variable L, which is the length of the column, and we need to solve for the unsupported lengths. So for the x-axis, since there is no lateral support along the x-axis, then we have the unsupported length is the length of the whole column. Meanwhile, for the unsupported length along the y direction, since we have a lateral support along the y-axis, so the unsupported length will be half of the total column height, assuming that the lateral support in the y-axis is at the midspan. Now for the slenderness ratio, we need to multiply the effective factor, K sub E. So there are cases wherein the effective factor for the x and y directions were not the same. So be mindful of that when solving for the slenderness ratio for each axis. So in order to get the slenderness ratio along the x-axis, we need to multiply the effective factor, K sub E sub x, multiplied by the unsupported length along the x-axis over the perpendicular dimension from the axis of buckling. So as you can see, we will buckle along the x direction, and this is the perpendicular dimension of the column. So we will have a value of K EX over multiplied by L over D sub x. Meanwhile, for the slenderness ratio along the y direction, so we have K sub EY multiplied by L sub y over D sub y. So since our L sub y is L over 2, since there is a lateral support along the y-axis, so we have a slenderness ratio for the y-axis of K sub EY multiplied by L over 2 all over D sub y. In order to determine the effective length factor that we will use for the slenderness ratio, so we need to check for the end support conditions. So for this one, the upper and the lower support conditions, both of them are translation fixed and rotation fixed. Meanwhile, for the second one here, the bottom support is translation fixed and rotation fixed. Meanwhile, the top support condition is translation fixed but rotation free. As you can see here, there's the top part of the column can rotate. Okay. Now for the third condition, the bottom support condition is that it is translation fixed and rotation fixed. Meanwhile, here the top support condition is translation free but rotation fixed. Meanwhile, here the pin-pin connection for the upper and the lower support conditions. So both of them are translation fixed but rotation free. So next is this one. So for the bottom support condition, it is rotation fixed and translation fixed. Meanwhile, for the upper support condition, it is rotation free and translation free. Meanwhile, for this one, the bottom support condition represents translation fixed but rotation free. Meanwhile, on the top support condition, there is a translation free but rotation fixed. So we were given two sets of values for the effective length factor. So we have a theoretical value for K sub E value. Meanwhile, we have a recommended design K sub E when ideal conditions are approximated. So the values for the K sub E that we will use in C133 is the recommended design when ideal conditions are approximated. So if we're gonna select this value of K and it is not specified which type of K sub E that will be used, then we will assume that the recommended design K sub E values will be used. Okay. So for the first four conditions, so we have side sway prevented. Meanwhile, for the last two conditions, this is when side sway occurs. Now, for most columns, pin connections are usually assumed at both ends. Thus, value of K sub E x and K sub E y are both value of 1.0. Now, for side sway prevented, as you can see here, for columns to prevent side sway, most likely their bracings are applied. Cross bracings are applied here. So buckling will still occur, but there will be no side sway. Meanwhile, for the second case or second figure, so you can see here that the column is tied to a shear wall. So this is the shear wall. Meanwhile, this is the column here. When application of compressive force and when it is connected to the shear wall, then the column will only buckle, but there will be no side sway. So for side sway prevention, so the effective length is less than the unbraced length. So this happens in frames with bracing or shear wall to prevent drift or side sway, and normally occurs on wood or steel frames. Meanwhile, when side sway will occur, as you can see here, the column loads P are applied on both columns, and we can see here that there will be side sway. So this occurs when the effective length is greater than the unbraced length. So this normally happens in rigid frames and normally on reinforced concrete and steel frames. Now, to determine the capacity of the column, so we have Euler critical buckling load P sub CR. So the minimum load, this is the minimum load at which the column first bows out. So in order to do that, we have a formula of P sub CR is equals to pi squared EI over KE over L quantity squared. So this value of P sub CR, so this is, we will consider the larger value of K sub E multiplied by L, since it will produce a larger denominator which will make the Euler critical buckling load P sub CR smaller. Okay. So dividing this with area, we will obtain the Euler critical buckling stress F sub CE. So F sub CE is equals to the Euler critical buckling load P sub CR over A, and we will be considering rectangular columns. So replacing the value of I with the moment of inertia for our rectangular sections, and for the value of A with B and D. So simplifying the equation will yield to a Euler critical buckling stress of F sub CE is equals to 0.822 E prime minimum over quantity of K sub E L over D quantity squared for rectangular columns. So next we have the Euler equation. So the uppercase f prime c is equals to the uppercase f sub c multiplied by the adjustment factor c sub d, c sub m, c sub f, c sub t, c sub I, and c sub p. So this provides a continuous curve over the full range of the slenderness ratio, as you can see here. So if the slenderness ratio is 0 or very low, the value for the f sub c will represent the pure crushing failure, as you can see here. Meanwhile, as the slenderness factor increases, so we will now have to consider the buckling of the columns. So the Euler equation is the one connects these two, so the pure crushing and the pure buckling failure modes. Okay, so in order to get the Euler equation, so we have f uppercase f prime c, so we need the column stability factor c sub p. So Euler equation describes the interaction between the two modes of failure of wood, so crushing and buckling. So pure buckling is defined by the Euler critical buckling stress, so f uppercase f prime f sub ce, and crushing is measured by uppercase uppercase f c asterisk. So it is the reference design value of uppercase f c prime without c sub p. So we need to solve first the c sub p. So the equation of c sub p is the 1 plus f sub ce over uppercase f c asterisk over all over 2c, where c is the values for c are 0.8 for solid lumber, 0.85 for round timber and piles, and 0.9 for glulam, minus the square root of the quantity of 1 plus f sub ce over f sub c asterisk all over 2 sub c quantity squared, minus f sub ce over f sub c asterisk all over c. Okay. So we have here a sample problem 7.4. A 4 by 6 10 feet column is subjected to a 15 kip compressive load, which is derived from the governing load combination of dead load and roof live load. Ends of the column are idealized to be pinned, and no relative translation between ends can be observed due to the presence of supporting shear wall. Lateral supports are provided at the ends, and to further increase the strength of the member, additional lateral support is provided at the midspan and the weak axis. So is the member adequate to carry the load? So assume normal temperature and dry service condition. The column is made of number 1 and better Douglas fir larch. Okay. So for sample problem number 7.4, we have here a column with a 15,000 pounds of combined dead and roof live load here, and it has a lateral support along the y-axis at the midspan. Okay. So for the strong axis, we have an unbraced length of 10 feet, and for the weak axis, we have an unbraced length of 5 feet, since there is a lateral support at the midspan of the weak axis. So for details of the column, we have 4 inch by 6 inch 10 feet Douglas fir larch number 1 and better type of wood, experiencing normal temperature and experiencing dry service condition. Okay, so based on the nominal section, so we have a nominal section of 4 inch by 6 inch. So you can see here 4 inch by 6 inch. We have any standard dress size of 3.5 inch by 5.5 inches. Okay, and we have an AG of 19.25 square inches. A requirement of the problem is the adequacy of this section. So for the solution, we first need to determine the governing slenderness ratio, or the higher value for the effective length over D. Okay. For the strong axis, we have an L sub x of 10 feet, value of D sub x of 5.5 inches, since it is the length of the dimension perpendicular to the x-axis, while we have value of case E sub x of 1.0, since it is a pin connection. Meanwhile, for the weak axis, we have a value of L sub y of 5 feet due to the application or due to the presence of the lateral support at the midspan of the weak axis. We have value of d sub y of 3.5 inches, which is the dimension perpendicular to the y-axis, and we have value of KEY of 1.0. So since the pin connections are assumed for both strong and weak axis. So to determine the slenderness ratio along the x-axis, so LE over D is equals to KE multiplied by L sub x over D. We have a value of 21.82. Meanwhile, for the weak axis, we need to get the slenderness ratio. So we have to multiply the KE sub y multiplied by the L sub y over D sub y. So we have a slenderness ratio at the weak axis of 17.14. So since both are less than 50, then the slenderness ratio is acceptable, and we will consider the larger value between the two. Okay, so in this case, the strong axis or the x-axis has the larger value of the slenderness ratio. So this is one that we will be considering. So next is we need to solve for the column stability factor C sub p. So we need to get the adjusted E mean, where it's equal to the E mean base design value multiplied by C sub m multiplied by C sub t and multiplied by C sub I. So for the E mean for the Douglas sphere large, number one better dimension number. Let's see here. Douglas sphere large, number one better. Douglas sphere large. As you can see here, Douglas sphere large, number one better. We have a E mean of 660,000 psi. So we have value of C sub m, since it is assumed of dry condition, value of C sub t, which is equal to 1.0 due to the normal temperature, and C sub I, value of 1.0 since there are no details regarding the incision of the column. So our adjusted modulus of elasticity, E mean is E prime mean is still 660,000 psi. Now we need to determine the Euler buckling force. So rather Euler buckling stress. So from the equation 0.822, E prime mean over the governing slenderness ratio quantity squared. Okay, so we have a value of the Euler buckling stress of 1139.66875 psi. Now we need to determine the leading equation for the FC asterisk. So FC asterisk is equals to FC multiplied by C sub D multiplied by C sub F multiplied by C sub M multiplied by C sub T and multiplied by C sub I. So for let's check for the wood if it's 1550 psi. So for the Douglas friction number one better, for F prime C parallel to the grain is 1550 psi, and the value of C sub D is 1.25 due to the normalized load it will yield the largest value, and for C sub F it is 1.1. Let us check the side value. C sub F for this one, so we have 6 inches width. We have a value of value for C sub F of 1.1 for F sub C. Okay, and value for C sub M, C sub T and C sub I is 1.0. So the adjusted value of SC asterisk is 2131.25 psi. Now, dividing this value, f sub ce over fc asterisk is 0.5347. And for the value of c is equals to 0.8 for Son-Lambert. So, getting the column stability factor c sub p. So, using this equation, we'll yield the value of c sub p of 0.575. So now we need to solve for the fc prime. So fc prime is equals to fc asterisk multiplied by c sub p. So 2131.25 psi multiplied by 0.4575 will yield to 975.16 psi. Now we need to solve for the actual compressive stress. So f sub c. So since there are no given data for connections, so we need to assume the gross area. Now getting the actual compressive stress along the column. So P over A is equals to 15,000 pounds over the area of the cross section, which is 19.25 square inches. So we have a value of actual compressive stress of 779.22 psi. Now we need to check for adequacy since this value f sub c, fc prime, is greater than the actual compressive stress, then the section, the 4-inch by 6-inch column is adequate against compression due to the 15,000 pounds load. Okay. For sample problem 7.5, determine the capacity of a stud wall, shown in the next slide, assuming that it only carries a vertical load combination of roof live and dead loads. The stud wall is composed of 2 by 4-inch members, spaced 16 inches on center, and is made up of mixed maple stud. The total height of the wall is 9.5 feet. Assume dry service and normal temperature conditions, and do not consider the bearing at the bottom and top plates. Express the capacity in terms of pounds per linear foot of the wall. So you can see here is the front view of the stud. So as you can see here, we have a wall sheeting here on both sides, and on the bottom we have a single 2-inch by 4-inch bottom plate, while on the top we have a double 2 by 4 top plates. Okay, so in the center we have 2-inch by 4-inch studs, which are spaced at 16 inches on center. So looking at the top view, as you can see here, here are the sheetings. The sheetings are and here are the 2-inch by 4-inch studs. Okay. For the solution for problem 7.5, kindly ignore this. The solution is for problem 7.5. The solution numbers have been swapped with respect to problem 7.6 on the slides. So as you can see here, the details of the problem, we have a combined dead and loop live load, and we have a stud wall here, wherein the stud wall has wall sheeting on both sides, and on the bottom we have a 2-inch by 4-inch bottom plate, while on the top we have double 2-inch by 4-inch top plates, and on the middle we have 2-inch by 4-inch studs, which are spaced at 16 inches on center. So looking here at the top view, we have here the strong axis as well as the weak axis, and we have here the wall sheeting where the studs are spaced at 16 inches, and since the 2-inch by 4-inch is the nominal section, we will be using the actual section in determining the capacity of the section. Okay. So other details were given to us, such as the type of wood that will be used is mixed maple stud. The studs will experience dry service condition as well as normal temperature conditions, and we also do not consider the bearing of the top and bottom plates. Okay, So our requirement is the vertical load capacity expressed in terms of pounds per linear foot of the wall. Okay. So since roof sheeting or sheeting is attached throughout the height of the wall of the stud, continuous or full lateral support is provided for the weak axis of the stud. Thus, the L sub y is equals to 0. So the column capacity is then evaluated by the slenderness ratio for the strong axis. Okay. So we have here the sheeting. So when we have considered sheeting, then the bending about the axis perpendicular to the sheeting is neglected. Okay, so in our case, since we have a roof sheeting, or sorry, rather sheeting here, so the perpendicular direction is this one. So the bending about this axis is the bending along the weak axis. Thus, it will not be considered. Only the bending parallel to the wall sheeting or the sheeting is gonna be considered in this case. So in our example, we have the strong axis. So we need to solve for the slenderness ratio about the strong axis of the stud. So the unbraced length of the stud in the x direction is equals to wall length minus the total actual widths of the plates. Okay. So for L sub x, we have 9.5 feet. We're gonna convert this into inches. Minus 3 multiplied by the 1.5 inch. So 3 because we have 2 inch by 4 inch plates. So 2 plates at the top and 1 at the bottom. And 1.5 inch is the actual B of the plates. So we're gonna use the actual dimensions of the plates. So we have here a value of d sub x. So here d sub x, here we have value of d sub x of 3.5 inches, and value of k sub ex is 1.0, assuming both ends of the studs are pinned. So L sub e over d is equals to 1 multiplied by 109.5 inches over 3.5 inches. We have a value, slenderness ratio of 31.29, so which is less than 50. So we're gonna compute for C sub p and FC prime. So first, we're gonna get the adjusted modulus of elasticity of the wood. So we have E sub mean after prime is equals to E sub mean multiplied by C sub m, C sub t, and C sub I. So E sub mean for maple, so mixed maple stud is 370,000 psi. Let's see here. Mixed maple under stud, we have your value of E sub E mean of 370,000 psi. So replacing the values of the variables in the equation, we have 0.822 multiplied by E prime mean over L sub E over D quantity squared. We have a value of FCE of 310.728 psi. Now next, we need to solve for the FC asterisk. So it is the base design value for F sub C multiplied by C sub D, C sub M, C sub D, C sub F, and C sub I. For F sub C, we have 350 psi. Let's check. Here, FC for stud of mixed maple is 350 psi. And we have here value C sub D equals 1.25 due to the normalized load. And C sub M is equals to C sub T is equals to C sub I is equals to 1.0 since normal temperature and dry surface conditions were considered, as well as no details with regards to the insulation was described in the problem. For the C sub F, we have a value of 1.05. Let us check here for the value C sub F. For studs, we have a value for f sub c of 1.05. Okay, and we have a value of fc asterisk of 459.375 psi. Now getting the ratio between f sub ce over fc asterisk equals to 0.676, and we have value for c of 0.8 due to the solid number. So getting the value for the c sub p is 0.545. Okay, so multiplying this c sub p to the fc asterisk will yield to the value for the fc prime of 250.581 psi. So now we know we need to solve for the vertical load capacity in pounds per feet. So we're gonna equate the actual compressive stress to the maximum allowable compressive stress to solve for the max load or the capacity of the studs. So capacity, so compressive capacity is equals to fc asterisk multiplied by a. So we have here 250.581 multiplied by 5.25 square inches. So it is the based on the dress load here, 2 inch by 4 inch. We have here the standard dress size and the area of the standard dress size. So we have a compressive capacity of 1,315.555 pounds, and we're gonna convert it into a unit length. Okay, so with W capacity, so compressive capacity in terms of linear feet is equals to P capacity over the tributary or width or spacing. So this, in our case, this is the spacing of the studs. So we have here 1,315.555 pounds over 16 inches, and converting this into feet. So we have here a capacity of 986.666 pounds per feet. Okay. In case of built-up columns, we will still follow the same procedure. However, for the value of C sub P, we have two values. One C sub P for the strong axis of each laminate, and another C sub P for the weak axis. So the smaller value of C sub P will be used to solve for FC prime. So this is done due to the required application of K sub F in the formula of C sub P. So as we can see here, we have D sub X, which is the column dimension parallel to the face of the laminations in contact with each other. So parallel to the face of laminations in contact with each other. So if the laminates are stuck in this way, then the value of D sub X will be here. D sub Y is the column dimension perpendicular to the face of the lamination. Since it is the face of the, here is the face of the lamination, so the perpendicular distance is here. So that will result to the value of D sub Y. L sub X is the effective length, column length for buckling about the x-axis, value of K sub K multiplied by Lx sub X. So here's the value of L sub X, and value of L sub Y is the effective column length at the y-axis. As you can see here, since there is a support at the weak axis, so the value for the L sub Y is reduced. Now the value of C sub P will be changed, so it will be now be equal to reduction factor K sub F multiplied by the quantity of 1 plus F sub CE over FC asterisk all over 2 sub C minus square root of the quantity of 1 plus F sub CE over FC asterisk all over 2 sub C quantity squared minus F sub CE over FC asterisk all over C. So reduction factor K sub F represents the measures of effectiveness of the shear transfer between the individual planks or laminates. So we have a value of K sub F, so 1.0 for the strong axis of the laminates, 0.6 for the weak axis if laminates are connected only by nails, and 0.75 for the weak axis if the laminates are connected by bolts. Okay. For the sample 7.6, we need to determine the adequacy of a built-up column made up of 4 3x8 planks which are connected by bolts. The column is 12 feet high and with pin end supports, and this to carry 100 kip compressive load, which is derived from the governing load combination of roof live load and dead load. Dry service and normal temperature conditions apply, so lateral support for both strong and weak axis is provided only at the ends. Lumber use is made up of number 1 Alaska hemlock. For sample problem 7.6, we have here a built-up column which is composed of 4 3x8 inches planks where it is laterally supported on both sides, on the top and the bottom, and is carrying a 100 kips combined dead and roof live load. So we have here since we have both unbraced lengths, since in both directions the planks are unbraced, so we have here L sub x is equals to L sub y is equals to 12 feet. So we have here a the type of wood that we'll be using is the Alaska hemlock number 1, and the column is pin supported in both ends. So the environment for the column is in dry service condition as well as in normal temperature, and planks are connected by bolts. Okay, so the required in the problem is the adequacy of the section or the built-up column. So here we have some notes. So first is that the orientation of the strong and the weak axis is the same for built-up columns and the individual planks or laminates. So in our case here, as you can see here, even though that the d sub y dimension at d sub y is larger than the d sub x, the strong axis still occurs or is still considered in the d sub x. Still considers it in the perpendicular direction of the d sub x. Okay, so next is the general computation for the column stability factor C sub p, and consequently the adjusted column design value FC prime uses the larger of the two slenderness ratios, so LE over D sub x and LE over D sub y. However, for built-up columns, the governing or the larger slenderness ratio may or may not control the evaluation of FC prime. We also need to consider the reduction factor K sub f, which accounts for the reduction of the actual column capacity due to the shear transfer between the planks or laminations of the built-up columns. So the K sub f factor is only applicable in the weak axis buckling. Okay. Hence, for built-up columns, we need to evaluate f sub c prime using both slenderness ratios for x and y axis. So we need to solve and compare the values of the column stability factor for the strong and weak axis of the built-up column. Okay. So first, we need to solve for the slenderness ratio. So we have a nominal dimension of the plank of 3 inch by 8 inches, but in actual it is 2 inches by 7.25 inches. So let us check here. 3 inches by 8 inches, so it's 2.5 inches and 7.25 inches. So we have here both dimensions of unbraced length for the x and y direction. So we have both 12 feet, and we have d sub x of 7.25 inches. Sorry, this is 7.25 inches. Meanwhile, for the d sub y, we have here value of 10 inches. So since the column being in a pin connection, in pin connection, it is assumed that it occurs on both axes, so in x and y direction. Thus, the k sub e x and k sub e y are both have values of 1.0. So solving for the slenderness ratio for the x-axis, so using the formula L sub e over d for the x direction, so L sub e is equals to ke multiplied by the unbraced length at the x direction. So as we can see here, we have a slenderness ratio of 19.86. Now using the same formula but in the y direction, so we have here the value for the L sub E over d y of 14.4. So the larger slenderness ratio occurs in the x direction. Now considering the strong axis of the laminates, so we need to determine the adjusted value for the E sub mean. So since we have Alaska hemlock number 1, here we have here an E mean of 580,000 psi. So since we have value C sub n is equals to 1.0 due to dry condition, C sub d is equals to 1.0 due to the normal temperature, and C sub I of 1.0 due to we have no details regarding the incision of the built-up column. So we have here the adjusted value for E sub E mean of 580,000 psi. Now solving for the Euler buckling stress for the x direction, you have 0.822 E mean over LE slenderness ratio in the x direction. So we have here value of 1,208 PS 0.511 psi, and we need to get the value for the FC asterisk. So it is the maximum allowable compressive stress without the column stability factor yet. So we have here F sub C equals to 1,100 psi. So let us see here. psi. We have Alaska hemlock number 1. We have value of F prime FC parallel to the mean of 1,100 psi. So we have value of C sub D of 1.25 due to normalized load, since we're given the dead and roof live load. C sub F is equals to 1.05. Let us check here. Okay. C sub F of 1.05 for F prime C. Okay. Next is that value of C sub M is equal to C sub T is equal to C sub I, which is 1.0. Since C sub I is also not applicable to glulam columns. Okay. So as you can see here, since C sub I, we ignore it because we have no details regarding incision. However, in the case that the built-up columns is composed of the glue laminated columns, so C sub I will not apply. The factor C sub I and the factor C sub F will not apply. Okay, so adjusting the value for the maximum allowable compressive stress, we have FC asterisk equals to 1,443.75 psi. So dividing the value for F sub C X and F sub C, we have a value of 0.83706, and we have value, and for the value of C we have 0.8. So we need to determine the column stability factor C sub P. Okay, so C sub PX is equals to 0.6266. So since the value for the K sub F is equals to 1.0, since we need according to the table, so according to the lecture slides, when we were considering the strong axis, the value of K sub F is equals to 1.0, and we have value C sub PX of 0.6266. Now we now consider the weak axis of the laminates. So we have here still 580,000 psi. So determining the value for the maximum Euler buckling stress, Along the y direction, we have 2,299.189 psi. And determining the value for FC asterisk is 1,443.75. So dividing the value of the two, we have here the value of 1.5925 and still value of C is equals to 0.8 and value of K sub F is equals to 0.75 since the built-up columns are connected by bolts, and we have a value of C column stability factor along the y direction of 0.6176. So we're gonna use the smaller value of the C sub B. So for C sub px we have 0.6266. Meanwhile for Cp sub y we have 0.6176. So we're gonna use this one, 0.6176. So now we need to compute for the adjusted column design value FC prime. So we have here FC prime is equals to FC asterisk multiplied by Cp sub y, and we have the value for FC prime of 891.781 psi. Note that even though the strong axis has larger slenderness ratio, which in general cases will govern in the evaluation of FC prime, the reduction in the actual load capacity of the column due to the shear transfer between the laminates has resulted to weak axis being more critical, thus controlling the capacity of the built-up member. Now solving for the actual compressive stress of FC prime, FC, we have here P over A. So we have 100,000 over 4 multiplied by 18.13 inches squared. So for the area we have N multiplied by the gross area of one plank. Okay, so we have N represents the number of laminates. So if the connection details are specified, such as the number of rows and bolt diameter, so the total net area projected should be used. Okay. So we have here 1,000. We have an actual compressive stress of 1,378.93 psi. Now, since F sub C is less than FC prime, as you can see here, FC is greater than FC prime. The built-up column made up of 40 inch by 8 inch planks is inadequate to carry the 100 kip compressing load.